All right, so let's get into this. So with the post on Piazza, let me get the title exact, just in case somebody's really looking for it and can't find it. It's 5 down from the top in the pinned post, lecture review topic suggestions. That's where I'm looking to get the suggestions for this week, and overwhelmingly today, recursion was requested, so we're going to go over recursion examples. I'm going to try to hit a few of the other comments as part of the recursion, so I am going to start. There was a little bit of request for testing. I'm going to start with some testing and show you off some test-driven development where we write the tests first and then the code. And also we're going to do some binary conversions, so those of you chatting about 191, hopefully this kind of doubles over and helps you study 191 as well. So for this, we want to write, and by the way, if you're upset, if you're farther behind and you want to review other stuff, I was expecting to review LO1 and 2 during this week, but there's just not a lot of noise in the Piazza about that. So I'm assuming the students who are very far behind just also are not watching lectures, are behind on lectures as well. So I'm not going to waste my time going over something that nobody's going to listen to be honest. I'm just not going to do that. If those students are that far behind on lectures, they'll probably watch the lectures that I've already presented on that material and get caught up that way. That's a better way to do it than requesting me to take everybody's time on something that they're not going to listen to, at least not until the end of the semester. By then, they'll probably know that stuff. Anyway, so that's kind of my rationale behind that, my thought process behind why those topics haven't been upvoted more. But if you don't like that, get your ass on Piazza and start voting. So I want to create a few things here. I'm going to create this as an object. And I'll just name it, I guess, binary conversions. And I want to write 2 methods going from decimal to binary and binary to decimal. And yes, we're going to use recursion. So this will cover the recursion, obviously the most requested thing. Somebody requested going over base cases, so of course I'll talk about that as well. And testing, somebody asked for testing and got a few upvotes. So we'll cover all 3 of those topics today, all those things in today's lecture. And then on Friday, maybe I'll take some of the lower upvoted. There are a few with like 3 or 4 upvotes that I might be down to those. I'm pretty much giving up on going over the slides this week. I think it's going to be more benefit to go over whatever you're requesting on Piazza. So let's do that. So for this one, I want to write a few methods. Let me just get the problem statements out there. I want decimal to binary, a method that's going to convert let me just get the setup. For some reason I always miss that R. I want to get a method that's going to converts binary numbers to decimal. Decimal numbers to binary strings. Example 10 is going to be converted to 1010. Or like 15. Let me get a different example. 16 is going to be converted to, oh my goodness, can I get this right? 1, 2, 3, 4. Right. So our 1's place, 2, 4, 8, 16. The decimal number is an int, and then return the binary representation of the input as a string containing 1s and 0s. So I got my setup for my method that I want to write. We know what we're supposed to be returning, and we want to just set up a stub of this. I'm going to go to the testing and try to test this method. So before I write anything, I have an error here, which means this isn't going to compile. I can write my tests, but I can't run them. I have broken code in my source folder. So what I'm going to do is just return some stubbed out value, in this case the empty string, just anything to shut the error up. Now I'm going to cheat a little bit. I'm going to duplicate this. And we're also going to go the other way, binary to decimal. Do the same thing, stub it out. Reverse these. The binary representation of as a string. These are reversed. We'll get some documentation on here. And converts binary strings. Oh my goodness, come on. I can't even click the right spot. To decimal numbers. Binary representation is a string. The decimal number represented by the input is an int. So we want to go from doubles to from decimal to binary, binary to decimal. I have my methods set up. They of course don't do anything yet, but now I want to set up my testing. I'm going to set up two test suite. There are two test cases here for each direction. So when we set up our tests, we can have as many of these tests as we want, as long as they have different names. When I say test suite, I mean the class, and that class can have multiple tests in it. I could even break these down for each test case. I could call the method once in each test and have like 50 of these, or I can just put everything in one like you see me do before in lecture. I can set this up in any way. So I'm going to break this down into the two separate methods. Normally I'd probably break this into two files, but just for the sake of the demo, I want to keep things a little bit more concise so I can get more on the screen at a single time. So for this, I'm going to create a map of all the test cases that I want. There's going to be a map of binary. Am I doing binary first? Sure. String to int equals some map with my test cases in here. So I'm going to start with the ones that I had in the example. 1010 is going to go to 10. And here's where I'm going to start the advice of how to do these lecture questions. Whenever I give a sample test case in an assignment for any question, that's got to be your first test cases. Like, that's a gimme. Just if you're given a test case, you better have that test case in there. For the first two homeworks, I gave you the pre-lab, and the TAs wrote up test cases in those pre-labs, and you had to write up those test cases. That's not always going to be the case. From homework 3 forward, we're looking at shifting things around a bit and doing that a little differently. But any test cases that you're given, you got to code those up. Like, code those up as test cases. Why wouldn't you? So the other one for 16, like, that's where you got to start. Now, the question on Piazza was, how do I know what else I have to test? Now, some of it's tricky the way I have my incorrect solutions. I have my cryptic hints, just making sure that you're thinking of everything. But in general, you just got to sit down and think about everything that can go wrong with a method like this. So, for example, the edge cases, if I just have 1, I better be returning 1. 0, I better be returning 0. And if the problem statement specifies any edge cases, anything that's very specific in the problem statement, like for calculator and microwave, there's a lot of kind of edge case functionality. What happens when this button is pressed when you're in this state? What happens when popcorn is pressed when the door is open? What happens when equals is pressed right after hitting an operation? Things like that. You need test cases for every single thing that's explicitly specified in the assignment, because if it wasn't important, I wouldn't put it in the handout doc. Like, those are important. These need to be tested. So for this one, we would have to ask ourselves, what happens when the empty string is the input? We can specify some behavior here. I didn't say what should happen in the description of these, so maybe we don't need to, but the way I'll code it, let's just say that empty string should return 0, so that better be something that we're testing. And a few more different edge cases. I should have been counting these. 1, 2, 3, 4, 5, 6, 7, 8. So all ones should be something that, that's easy to screw up, as I screwed up. That's something easy to screw up if you have just a whole bunch of ones. That's something that you can certainly go wrong. Let's add 1 to that. And this should be 256. So a 1 and then just a whole bunch of zeros. Let's make sure we're handling that. And hell, while we're at it, what if we have some leading zeros? What if we have 7 with a bunch of leading zeros? That's something that's a valid input. We need to find the decimal representation of that. But it's something that we could code wrong. If I have a bad test case that says doesn't handle leading zeros, or leading zeros bad, or something like that, so anything that says leading zeros in it, that's your hint that you don't have a test case with leading zeros, if this were a lecture question. And then let's leave it at that for now. That I'm comfortable with that. Maybe we could have another test case with a very long binary string that starts maxing out. Oh, why don't we do it? Oops. Why don't we add that one more? So a really long binary string. Just to make sure that we have everything working right. And I'm going to cheat a little bit. I'm going to go online. Use a calculator. To get my answer for this one. And for test cases, it's very important to violation. And I won't study. Are you saying you should push this instead of usually? I'm assuming that's an autocorrect. I will push this. I'm coding in the examples repo. I'm gonna hit this check mark when I'm done, and you're gonna be able to see this. And let me make sure I didn't overflow an int. Looks like I'm safe. There's less than 32. We can see the exact binary representation of the int. And you know what? Let's add some leading zeros here just for good measure. So if there's fewer than 32 bits here, then I know, or 31, including the sign bit, then I know I didn't overflow an int, but I don't feel like counting those, so I'm just looking at that to make sure. So we have our test cases. We're testing one very large input, making sure that, and complex, making sure our logic is sound. Some kind of edge cases, all ones and mostly zeros. Leading zeros, the base cases that are going to end up being our base cases of our recursion. We got all our kind of specific things handled there. So we might be able to add more cases here. There might be some specific things that we want to test, but this should cover pretty much anything that we're going to need. This is going to get us covered for, if this were a lecture question, this is going to cover any of the bad cases that I would put up with. Maybe I'll have a bad solution that doesn't handle consecutive ones or something, or consecutive zeros or something. This is going to hit anything that I'm going to come up with for incorrect solutions. So now that we have our test cases, we have to have an assert. So I want to iterate over my map, so I'm going to iterate over the keys and values at the same time. So for input, output, in my test cases, assert, what do I call it? Binary conversions dot binary to decimal of the input equals the output. And then if that's false, give me the input I'm going to break this into 2 lines because I need to reuse this value. This is a good 115 question. Why use a variable? My standard answer is if I'm using a value more than once. I want to compute it once, store it in a variable, and then use it in multiple places. So the computed output of my method was this. And then if assert that the computed output equals the expected output. If not, print out the input and the computed output for me so I know what actually happened there. And I missed a plus sign. Since we're just doing the reverse here, everything's just going to be... Oh my goodness. I can do this. Everything's just going to be backwards. We'll see if I can read chat while doing this. Probably not. If you highlight the binary number, then in the footer... Oh, really? Oh, it shows how many characters it is. I thought you were going to say it does the conversion and shows me what it's going to be in decimal. But yeah, let's... 33 characters. That's with the leading zeros. So that's a really good test case. 30 characters, I'm pushing the limit of an int, and then adding extra leading zeros that push me over the limit for an int, just in case I'm doing something funky with ints. Some students like to use the Scala built-in functions for this. That's a good test case that might break those functions. Since you can just go, you can actually do that to int Well, now I'm committed. I think it's int dot integer dot to binary string. Do we have a from binary string? Well, the method exists somewhere. I'll give it one more try. String dot binary. No. But there is a way to do conversions. And let me get rid of this stuff. And everything else is the same, except I have to call decimal to binary. The input, and this backwards. So one of the nice things of loops, I have to change all my test cases by hand. In your test cases, I started saying this, I don't think I finished it. Your test cases should be hard-coded. You can't use your code, or at least you very certainly shouldn't, use your code to generate the test cases. Because if your code is wrong and you're using the test to test your code, but you're using your code to generate your tests, you have this cyclical dependency, and you have your code generating bad test cases that only your code is, technically correct on. Only your code passes those test cases, but correct code does not. That's why I always run your tests against my correct solution to make sure that your test cases themselves are valid. If they're not valid, and especially if you did something silly like used your code to generate your test cases, it's just no good. So that's why I went to that website to generate that, to do this conversion. I want to use something else that's trusted. I believe that website is going to convert binary properly, or else they wouldn't be the #1 hit on Google when I search for that. So I'm confident that I do have the proper conversion here. So I have my tests. I can run this test suite, or I could run each individual test, and if all goes right, these should fail horribly. I didn't have any pop-up menus yet. I'm in the habit of avoiding them whenever I can, except when I open the project. So now I have the first test case that's tested. 0 did not equal 255, so the library is helping me a little, giving me some description. But then after that, it's going to show my output string. On this input, all ones, the computed output was 0. It's obviously not what I want. For the other test, decimal to binary, on the input 1010, or sorry, on the input 10, I didn't return the right value. I didn't return 1010. I don't know why that's in brackets like that. Did I mess something up here? But I want this hint text to be able to help me out. So I got my test set up. I looked at all the edge cases, thought about everything that could go wrong with this. Got my test cases that I'm happy with. Let's get to some recursion. Let's do it. Do we want to start with decimal to binary or binary to decimal? Probably decimal to binary. Let's do this one first. I think that a student could cheat on the LQ and try to write tests to prevent it. I forget what you're referencing, what I said you're referencing. All right, recursion. So a few things here. We're going to go through our list of 3 things. The base case, some trivial input-output behavior. We want our recursive step. So whenever the base case isn't hit, we're going to go to our recursive step. That's where we're going to write logic, assuming that our method is already correct. And we're going to make sure any recursive call is always getting us closer to the base case. Would be 2 binary string. Example 3.2 binary string. Okay. How did that not? Oh, because I was trying to go the other way? I think I found that one, right? 2 binary string, but I didn't find the other one to go from a binary string to a decimal representation. So, yeah, so this one would be easy. I would just do, if somebody were to cheese it, I've had this happen in the past, I've had this question before. 2 binary string, run my tests. And it actually didn't work. Decimal to binary. 0 to 0 is what I would expect. I think I have something going on with this test. What do I have going on? Map of int to string. Oh, these leading zeros wouldn't be there, first of all. This isn't a valid test case. I should have looked these over first. Oh, it looks like that was the only one that was wrong. And let me reverse these test cases. It's bugging me that I have my tests in the opposite order of my methods. All right, so now we passed. Only test binary to decimal is showing up now. Decimal to binary is working. So we completely cheesed the question, go us. I'm just out of curiosity. I wonder if this is written as recursion, recursive method. I'm giving up on that rabbit hole. All right, so let's start our method for this. We need our base case, our 3 steps. So let's start with our base case. I'm going to say if decimal equals 0, 0. Easy enough. Else, if this is a case where we're going to need 2 base cases, if we just say if decimal equals 0, it's going to be tough to always make sure we're getting to our base case. Because what if we have the string that's all ones? What if we have a 1 somewhere where that's going to hit our base case? So if it's not 0, it might be 1. We want to return 1. So we're checking any input that's going to give an output of length 1, a string of just length 1. That's either 0 or 1, and that's it. Else, we know we have an an integer that's greater than 1, and, you know, for good measure, we could add, I'm not going to bother actually, we could add some way of handling negative numbers. We could actually convert negative numbers to binary, but we're not doing that today. But we could add that to the spec of the question. Let me add it right now. No negative inputs. There, I cheesed it just like students do. So now we want to write our recursive case. Now we want to come up with some logic where our logic is sound, assuming that decimal to binary actually works. So we know we're going to have a recursive call in here somewhere. We're going to assume that recursive call is going to return the right language. Or the right language, I'm mixing chat. The language is Scala, JB Rises. And we're going to assume that our recursive method is correct and that it's going to return the right value. And we have to organize our logic in such a way that we're always going to get closer to the base case. So if decimal to binary is correct, what can I do to get this closer to my base case, to organize my logic and make my recursive calls closer to the base case and have all my logic be sound? That's my goal, and that's your goal when you're writing the recursive step. The base cases should be trivial. Those should be easy to write in most cases. It's this recursive step where you have to juggle a few things. How do I get closer to my base case and be correct? I'm going to do this by checking if my decimal value is even or odd. I'm going to make some decision based on that. If it's even, I want to do something. If it's odd, I want to do something else. So if it's even, if I have an even number, that means my binary representation is going to end with a 0. So this is going to be equivalent to that decimal, that input value divided by 2, that binary representation, oops, I did this wrong, divided by 2, then append a 0 to the end of it. So if I take half of this value, that's effectively shifting all the bits to the right. And in fact, I'll show you a trick. Actually, I don't want to, I'll erase this before I push. But I want to shift this to the right by 1 value. To do a binary shift on an integer, we can use this syntax, shift to the right by 1, and append a 0 to the output of that. So say my input is, let's use 10 from the example. Say my input is 10. This is going to be the same as 5, which is 101, with 0 appended to the end of it. So I'm going to divide this by 2, which gets rid of this least significant bit of 0, gets rid of that, uses this as my recursive call, and then whatever that returns, use this as my recursive call rather, and whatever that returns, which we're going to assume that we're going to get 101 because we're assuming our method already works. We're just assuming it works. And then we're going to append 0 to that. And guess what we do when we're odd? Same thing, we just append 1. So in this case, say we have 5, which is 101. We're going to shift that to the right 1, which is going to give us 2, which should return 1, 0. And we're going to append 1 to the end of that. So we want to get rid of this least significant bit by dividing by 2, getting that smaller value, making the recursive call, assume that recursive call is going to be correct, and then append that least significant bit back in. And we're done. That test didn't fail. It's only the other one failing. We're done. Effectively 4 lines of code. 4 lines of real logic. 2 of them are base cases. Then we just split it into even and odd and just come up with some logic. How do I break this down into a problem that's closer to the base case and then have some logic that's going to get me back to using that solution of the recursive call, grow that into something that's going to be a solution to the original call. That's it. And usually this is the case with recursion. You feel like you haven't done any work. You do a lot of work. It's kind of like the state pattern. You do a lot of work in the design, but you don't do a lot of work in the coding. The coding gets pretty easy once you have a design. So the right shift operator, the arrow, I'm going to get rid of that. I just want to show you for those of you who really want to see some cool stuff. But that's the same as a division by 2, an integer division by 2. It's a bitwise shift to the right. Something you've probably seen in 191. I don't know if you can see that in 191 anymore. But if I have this as the binary representation of my int, I'm going to shift it 1 to the right, which is effectively a division by 2 and gives me this. It just basically erases the least significant bit. And same here. If that bit's a 1 or a 0, it just erases that least significant bit. And I can do, like if I want to divide by 4, I'm going to shift by 2 bits. If I want to divide by 8, I'm going to shift by 3 bits. And it's a very efficient operator. So when I code that and I want to do division by 2 or multiplication by 2, I use bit shift operators because they're way, way faster in the CPU than division by 2. Division by 2, it's got to pull out some big guns and actually do a full division, which is way more expensive. If you say, hey, it's just a bit shift operator, the CPU can just go like, oh, I'm going to erase that bit. Done. Like 1 clock cycle. Division takes quite a few clock cycles. But division by 2, this will be integer division. It'll have the same effect. It'll remove that trailing, that remainder of 1. So that's it. Our method is over. We have our recursion. It might not look like too much, but the design that goes into it, that's what you're feeling. The design is a bit trickier. Let's go the other way. We have a binary string. So let's say if we do have our base case, if binary.length equals 0. We did say empty string is going to return 0. So let's do that. Else if binary.length equals 1. Binary dot, I'm going to get a little fancy here. I'm going to create it to an int. This is covering either 1 or 0. And that 2int's going to give me the right value. 1 or 0 in binary is the same as 1 or 0 in decimal. No, nothing to do there. And then the recursive step. What if we're not hitting one of our base cases? Our base cases are based off of length. So we want to trim the length of this string down. So I want to do the same thing here. I want to handle this 1 bit at a time. So if I'm handling this 1 bit at a time, how am I going to get this working? Let's use the same example that we have up here. Let's say our input is 1010, or which should return 10. How are we going to make some recursive call to make this work? So what I'd like to do is do the same idea that we did up top and give the input of 101 or 5 to the recursive call. So I want some recursive call, binary to decimal, of this input string, but without that least significant bit. We've seen substring before. Let's go from 0 to binary dot length -1, exclusive of the endpoint. So that's going to trim that least significant bit off of my input string. And we're going to assume that this call is correct, that when we give it 101 in this example, this is going to return 5. And to go from 5 up to our 10, we're going to see that this was a 0. So let's multiply that by 2. This is our odd case. So if binary dot char at binary dot length -1. This is where you really have to know your indices. Equals 0. So a few things here that I do have to explain. This is all going up here, first of all. Oh my goodness. Fingers, work with me. Or 2. So this is when the least significant bit is 0. I'm going to make the recursive call without the least significant bit. So I'm kind of doing the same thing as the shift right, but with strings instead of ints, and then multiply that by 2. So if I get this value, this representation, and I multiply that by 2, which is a shift to the right. So by the way, I could do the same thing here. Shift to the right by 1 is going to work well for me. Just to reduce the new syntax, I'll do ×2. But here, if I'm getting a character, this is going to be a character, not a string. So if I have double quotes here, this is going to give me, oh, it doesn't even give me an error. It just gives me a warning. Because I'm comparing a character and a string, just usually something we don't really want to do. If you use single quotes, that's a character in Scala or in Java, any Java-based language. Single quotes is for a character. So since I only have a single character that I'm comparing to another char, I'm going to use single quotes there. So if that's a 0, our logic is sound. If this is a 1, so if our least significant bit is 1, we're making a recursive call. We're assuming that's correct. Now we have a little more work to do. We want to take this. Oops. No, this is right. Multiply it by 2. And just slap an old +1 on it. Green bar. Dunzo. Yeah, so if the last character of the string is a 0, then we know we have an even number. Every other binary bit is a power of 2. There's no way we can sum up powers of 2 and get an odd number. This is the only way we can get an odd number is if the least significant bit is 1. So we guarantee that's an even number if the least significant bit is a 0. Else, then it has to be a 1. There's only one other choice. So my else is we have an odd number. And we could probably condense the code down a little more and get rid of the conditional, but there's no need to. If we did like plus, actually I know how I would do it. If we did this dot to int, then it's going to be a 0 when I need it to be a 0. It's going to be a 1 when I need it to be a 1. But we don't have to get that fancy. Green bars. And both of our things are basically 4 lines of code. You can imagine how you would do this with a loop. You'll get it done, but it might be a little messier. It'll be the same logic. You'll do the same conditional. You'll do this inside a loop. But with recursion, it kind of takes away some of the work that you have to do, as long as you're thinking of base case, trivial input output, recursive step, design an algorithm that's going to work under the assumption that your recursive calls are correct and you're always getting closer to your base case. We're always calling this with a string that's a little bit shorter, 1 character shorter than the input string, and our base case is based on length, so we're always getting closer to our base case, and our logic was sound. If we're even, it's that recursive call times 2. If we're odd, it's the recursive call times 2 plus 1. Dunzo. So I'll watch for more questions on this while I set up the next thing, if I remember what it is. Oh my, would we go till 2:40? There's no way I have time for that. Whatever, let's do it. Let's try. Is it okay just to call this min? I created a Java class. Is that real? I did do Java class. Min of function. I want to do this one because it's cool. I don't have, my notes are just what the problem is. Find the min max 0 of a function. I'm just going to do min. So this might go wrong, but let's try finding the min of a function. So check this out. Double to double. Double. And this one will help with your genetic algorithm, so I want to go over this one. Finds the input of the minimum output of a function. The function to minimize the input value with the minimum output. One. So that's what we want to do. How did he do that? Which part? Can we do recursion, please? Oh my goodness. You should use the triple colon syntax. Yeah, not working with a list today though. For recursion. Or are you answering somebody else's question? Can I explain how tomorrow's lab will go? It's LO1 makeup lab, so it's exactly like the LO1 not makeup lab. It's exactly like the original. If you skip the original, I'm not spending the time to explain it to you. Like, just go to labs when you're supposed to go to labs. Test min. Test min of a function. The comments. How did he do that? The comment. Oh, I did a slash star 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 and then enter, and it'll give me that syntax. It'll add the Java doc syntax for us. I guess technically Scala doc now. So it'll add for each parameter. It'll give you what that is, what the parameters are. It'll set that up for you, and then the return value. And then this will you can create nice documentation based on this syntax. As it was pointed out a few lectures ago, so I decided I'd use it today. But you can use HTML in here, and then use tools that'll generate nice looking documentation for your code. We're just doing, yeah, the Thursday lab, tomorrow's lab is just LO1 makeup. If you have credit for LO1 read and AutoLab, then you don't have to take tomorrow's lab. If you have credit for that, you only have the homework interview, which is scheduled with your TA. So you don't have a homework lab tomorrow. There's no homework lab tomorrow. It's only LO1 makeup lab. Yeah, you could do to-dos as well. If you use to-dos, I don't know if I have it right here. You can get a list of all your to-dos. Looks like I have some in this project. You can get a list of all your to-dos, so when you have a large code base, it's easier to find where all your work is that you have remaining to do. Very useful stuff when you have large projects. Okay, but let's get going with this. Test min function. I had one in mind. Let's try to do this quickly. Val f of type double to double equals x of type double to x squared. Let's do 3x squared plus 4x minus 2. Format it. Double needs a capital D. And min of function f should equal, good question, what should this equal? And I'm going to go to this wonderful thing called the internet. I'm going to forget like 8 times what my function was. I think it was 3 plus 4. Oops. The constant won't matter, but I think it was minus 3. Did I get that right? Oh, I'm in the right window. 3, 4, negative 2. 3, 4, negative 3. Close enough. And that would have gave me the same min according to our definition. And I want to look at the min value, and the x value is minus 0.667. So let's go to IntelliJ. I expect this to be minus 0.6666667. I don't like magic numbers, so expected equals 0. To be exact. So it's negative. In less than some epsilon. Looks good. The few, the proud, the strong. Yeah, all that's in the syllabus too. I have lengthy explanations in the syllabus. It's like the 3rd section of it. What read, write, explain, verification, what they all are. Verification is just me putting my final stamp of approval on it. Just in case something weird happened with grading, I might ask you to do something else. I haven't used that yet, but towards the end of the semester when there's a mad rush to get everything in, I might have to use the verification. All right. So this gets tricky. Min of function, right here, there's not a lot we can do with this. So this is a much trickier question. And I'll try to get through this example I'll use up the 20 minutes between. So I guess technically it's not part of lecture, but this whole week is just to help you out anyway. So if I'm helping you more, you know. But let's try to do this. This isn't going to help us much. We don't have any information to work with. We just have the input function itself. So this is a case where we're not going to be able to write a recursive function directly, or a recursive method directly. Similar to your genetic algorithm, for those of you who took a peek at that so far already, it's you're not just going to be able to use the method header that I give you and just write a recursive function with that. It's not going to work. What we need is a helper function. I'm just going to call it min helper, which gives me some extra information to work with here. So I'll still need the function itself, but I want a little more information. I want to know where I'm looking. So this function is going to search for a min, and we're going to do a hill climbing algorithm. We're going to start at some value and start looking around that value for something that's a smaller value than what I found. So what I want to is input is the x value of the minimum value that has already been found. Let's leave it at that for now. I will want another one, but I want to show you my thought process as I go through this. And then I want to call, this is just going to call the helper function with that function. And let's say we're going to initialize at 0.0. That's where we're going to start our search. So we don't want people calling this method to have to worry about giving this xMinFound, which is just a helper variable. It's going to help our recursion actually do this search. So when you want to find the min of a function, you want to just give it a function, but we're immediately going to defer to another function with all of the recursion parameters that we need. So we can start passing values down the recursion and have our recursive calls communicate across stack frames through parameters and return values. So I want to set up this extra parameter to be able to communicate across recursive calls. So if and then I want to check a few things. Let me set up the recursive step before we get into the base case. So the recursive step, I want to do a few things. I want I'm going to initialize some step size. You should get some flashbacks to calculus when seeing this. Some step size, which is like our DT. I'm going to set this to 1.0 for now. And what I want to do is look forward from where I'm currently at. So if xMinFound is the best x from any recursive calls up the stack, all these frames, whatever frame called me and above, whatever the minimum value found, the x value for that point, I'm going to get that as a parameter. So when I get that xMinFound, I want to look forward in x and backward in x and compare that to the value at x. So if f of x plus this step size is some value, I'm currently looking at f of xMinFound, or I could also go backward. Oops. Equals f of xMinFound minus step size. So this is where I'm currently at this level of the recursion. I don't know what happened before we got here, but this is where we're at. I want to look ahead and I want to look back by incrementing and decrementing x. And I want to know which of these three values is the minimum value. So I'm going to have three separate cases. And just to visualize this, we're going to start at x equals 0. So for this case, I would start right here. And I'm going to look forward 1. Got to zoom out a little here. So I'm going to look forward 1 in x. So I'm going to compute this value. And I'm going to look backward 1 in x. So I'm going to compute this value. And I want to know which direction I should move in. So in this case, I'm going to move this way because this is the min value. So I know the min is going in this direction. At least a local minimum. We could have a cubic equation where there, to the fourth or something where there's multiple mins and multiple maxes and stuff. We could have a lot of stuff like that. But we're going to at least try to find a local. We're going to find a local minimum if one exists. That's what this method is going to do. So we're going to move here, and then we're going to do the same thing. Look ahead, look back, find the min, and then slowly try to get closer to this minimum value. But right now we're just looking which direction should we look in by looking ahead, looking back, and looking where we're at. And eventually we'll get to a point where we're looking here, here, and here, and the current point is the minimum of those three. And that's when we can start decreasing the step size and start narrowing our search instead of jumping by 1x all the time. So that's our goal that we want to accomplish. So we have 3 cases that can happen here. If current less than forward and current less than backward, then we can start narrowing and specifically we want to decrease our step size at that point. Parentheses mistake. Oh yeah, there is. This one's the mistake. I want to add to X, not Y. Thank you. So if that's not the case, I want to check if forward is less than backward. In this case, I want to move forward. And the only other possible option is move backward. Okay. So here are our cases. If we want to move forward, let's do these ones first. If we want to move forward, we're going to make a recursive call min helper f x min found plus step size. If we want to move backward, minus step size. There's a big problem with these two that I wrote, and if you've been listening to my 3 steps, you should see what it is. There's a big problem here. Oh, I might as well just say it. We're not getting closer. Oh, I was going to say we're not getting closer to any base case, but I haven't even written a base case yet, so that's not very evident. And if if the current is the minimum out of these 3, we want to narrow our search, and you're just going to have to take my word for this one. We want to decrease the step size by 2/3. And by the way, for a decent example of this similar logic, you can check out in the genetic algorithm, the what's it called? The aimbot code, the cost function of that uses the same idea. It has a recursive cost function, which does this similar thing. What we want to do is decrease the step size by 2/3. So going back to our other example, our visual here, if we're somewhere around here, let's say, and we're checking here and here, and this is our minimum value, we want to start narrowing our search to be able to get closer to this value. The next check we want to do might be like here and here, and we want to move over here. Check here, and then check here and here, and slowly just narrow our focus right on this. So each time the current value is the min of these 3, we're going to narrow our focus by 2/3. We're going to decrease that step size. But we can't really do that the way we're set up right now. So to do that, I want to add another parameter here. This is something that has to change across recursive calls. 2/3 so if you move, if you're in the current and you decrease it by 2/3, and then you either go left or right. Actually, I think we can get away with 1/2 the way I'm going to set this up, the way I'm thinking this out. Let's try 1/2 and make sure we don't get jammed up there. Yeah, that should work. This should work. It's 2/3. I was thinking the way I have aimbot set up, I have to use 2/3, just the way that I go forward, and if I overshoot, I go backwards, but also decrease the step size. So I don't want to exclude any parts of the solution space. I think 1/2 works here. So since the step size has to change across recursive calls, we're just going to throw it up here. This is something that can change, so that's going to be another parameter in our recursive call. It's an easy way to make things change across recursive calls. Just make it a parameter. If it doesn't change, like f, whatever, we're just still passing it anyway. Can't hurt to have too many parameters here. But step size, we want to change it. We're going to make that a parameter. And then we can initialize that parameter in our top level recursive call, the one that just defers. So we're going to start at x equals 0 with a step size of 1. And then the step size and xmin found are going to change as the current, I should just call this the current that we're looking for, that we're looking at. And these are going to change across recursive calls. So if current is the best that we have, if current is the best that we have, we're going to do min helper of f. F is never changing. X min found didn't change in this case. And step size over 2. Just force a habit. I always put my 0.0 because I absolutely want to avoid integer division here. That would just destroy everything. Step size is already a double, but hey, I'm just going to be extra safe here and make sure nothing strange is happening. So our logic seems sound, but we don't have a base case yet. So there's one thing we can do here. Since our step size is decreasing, we're narrowing our focus as we're getting closer to this local minimum. Yeah, that's fine. Once my step size is at some precision that I want, I'm going to stop. Now there is a danger here. If I'm not approaching a local minimum, these two recursive calls actually don't get closer to my base case. So I am running a risk of infinite recursion and stack overflows here. Actually, not stack overflows, but I am running the risk of infinite recursions here. If these are not actually getting closer, if I'm never actually getting closer to a local minimum. So for example, if I have a line, if the line is an input, I got infinite recursion here. I'm just going to constantly go further and further in the negative direction. Never decrease the step size, and I will go infinite. So this is not a great solution, but it is the solution we're going to go with. Auto format. But as long as we're close to a local minimum, then we're going to be decreasing that step size, and we're gonna quickly get to this step size. So let's run test min. Pass. Let's put our epsilon precision. If epsilon is too small, we might exclude correct solutions. I always say that. So let's see an example of that. This is too small of an epsilon. It's very direct here. It's smaller than my precision that my recursive algorithm is stopping at. And we can see this this absolute value difference. It needed to be 1 to the minus 8. It was 4 to the minus 5. 4 times 10 to the minus 5 scientific notation. I'm sure you're familiar with. So we just weren't precise enough, but this was the difference between the expected and our actual computed. So we're doing all right here. We swap this out for a line. Oops. If we just do 4x minus 2, our expected output is negative infinity. And we're going to get the wrong answer here. Or actually, we're not going to get the wrong answer. We're just going infinite. You'll notice that fun little tidbit. You'll notice that this is not an infinite recursion. It is just thinking and thinking and thinking. And that's because we have what's called tail recursion. The compiler actually unrolls this recursion into a loop. Because the recursive call is always the last call of our method. but that's not something we really have to worry about too much. But we effectively have something that can find the min of just any function that takes a double and returns a double. So a local minimum, if one exists, I should say. We can add a few conditionals here, actually. Let's define some bounds. If we're super huge, double dot positive infinity. My goodness, I wish I could type. Less than negative infinity, else. One brace missing, auto format. Rerun the test. Guess we can I'll do the old 1-1. There's no precision errors when you're talking about infinity. It's either infinity or it isn't. Oh, what now? Oh, yeah, my precision. What now? I purposely broke it. So I was doing negative infinity minus negative infinity, which gave me not a number. You can't compare infinities like that. It's not going to give me negative infinity as or 0 as a return value. So that's why that broke the first time. I have to actually check for equality. Is the output actually equal to negative infinity? It is. It's working. We have our code. Submit that. Do I have to do this again? I didn't push. Oh, no, I did push something last time. In recursion examples. Push. One thing to note, I'll mention this now. I'll add it to the doc. I'll add some test cases and stuff. But but you should be careful with this base case in your genetic algorithm. You're not always, so you're minimizing the score function, but you're not always going to get a score of 0. There will always be a solution of 0. So you have to be careful with what you set up as your base case in that. I'll give some test cases in the doc. I'll add to that. Since it looks like we won't have a pre-lab on that, I'm going to add some test cases to the doc to make sure that's clear. So just check the doc when the time comes. And that's some healthy dose of recursion today. Hopefully that helps. I used the helper in my recursive factor as well. You can actually use 2 helper functions. It's even cleaner. I only used 1. I used a list to collect all the factors. But some people do 2 recursive helpers, where the other one is a method that just tests for one potential factor, and then that one keeps getting called by incrementing that potential factor. And then the other helper accumulates all the factors in a list. This is good stuff. Good stuff today. I think those lectures are... I enjoy those lectures. They're fun. They keep me on my toes a bit more. Alright, but let me check. Just do one more scan of comments and then 4:42 time. Yeah, the helper method with an extra parameter, because I don't want to expose my stuff. What's the more formal way? What are you talking about? So like if you were using access modifiers, that helper function would be a private, or that helper method would be a private method. That's not exposed to anybody else. Those are internal details of the working of my algorithm. And then the top level one, that's like what you're writing for other people to call. So like when I give you a lecture question, I'm saying, I need a method that does this. It's up to you to build it. I don't care about your internal details. Your internal details might make use of a helper method for your recursion with extra parameters to get your recursion to work the way you want it to. But you can't add those extra parameters to the outside world, what the outside world is going to call. In the aspect of the course, that's my autograder. My autograder is going to expect a certain parameter set. But out there in the real world, it's going to be other, your teammates, other people calling your method, and they want that method to be easy to use. They don't want to have to care and read your documentation, care about what all your helper parameters are. Nobody wants to do that. So you hide those details and expose a public interface as the method with the minimum number of argument of parameters. The same thing is true with like sorting methods, how it takes a comparator that compares two things. You might have another comparator method. That function might call your helper function that you wrote to be able to actually get the job done. But nobody else wants or needs or can be exposed to those extra parameters because all the sorting functions just take two inputs and compares those two values. Should this value come before this value? That's it. It can't say, does this value come before this value? And also, here's a helper parameter that I need. It breaks everything. You can't do that. So you got to follow the interfaces of what's being expected of your method or function, depending on the example. Monday, man, we could. So yeah, going off of that, it could have been done in a single method. Oh, UB Alex was responding to you. I see. I shouldn't go backwards in time when I read the comments. Yeah, it could have, but the problem statement is find the min of this function. So that's what I wanted to deliver to my end users. Just give me a function and I'll find the min. But to set up my recursion, I needed those extra parameters. So I just had my public facing method, which just takes a function, immediately defer to my function with the extra parameters, and I gave it some default parameters. You don't want the end user to have to think about what your default parameters should be. Don't make them think more than they have to.